All right, we've calculated the potential of a lot of different cells, and that's the potential difference for an electron being with one metal versus being in another, and you just look at your standard reduction potentials and figure out which element is better at losing electrons versus the other one gaining those electrons. And it's straightforward. But your standard reduction potential sheet, you get like one of these for AP chemistry, list of the metals, every time, a list of metals and a list of potentials. These are standard reductions. So these are always if you have 1 molar solutions and if it's at 298 degrees. And if there's a gas involved in one of the electrodes, like the hydrogen electrode, then that's at 1 atmosphere. So let's look at how you can calculate if you're at non-standard conditions. So if you're at non-standard, you're still going to look at the potential difference of the standard cell. So use your metals, find out what their standard reduction potentials are, figure out which one is actually going to be oxidized and not reduced, and that gives you this. And then you're going to adjust that amount using this guy. So this whole thing right here, the potential difference of a cell is equal to the potential difference of that cell under standard conditions minus RT over NF times natural log of Q. This is the Nernst equation. So the R is going to be our gas constant. There's several of them, so to figure out which one is going to relate the units we're using, let's look at the units we're using. T is going to be temperature, and yeah, we're going to want to use Kelvin because Kelvin is the one that's based on movement and is based on entropy. If you go down to absolute zero, you have absolutely zero movement. So temperature in Kelvin, so that's one of our units. N is going to be the number of moles that are transferred in your balanced reaction. So you know how we've been looking at one metal is oxidized, one metal is reduced, and if we write the balanced equation, we might have in one step a metal is gaining 2 electrons, and the other step a metal is giving off 1 electron. We've been balancing those electrons, but that hasn't affected the potential. The number of electrons goes here, so it does come into play somewhere, and also comes into play if you're calculating the Gibbs. So okay, so your number of moles of electrons transferred in your balanced reaction is here. F is, it's actually like a fancy curly QF. This is Faraday's constant. It's a constant. Constants don't change. That's nice. It's always going to be 96,500 coulombs of charge are carried per mole of electrons. Okay, so now we know we've got the unit coulombs. We're dealing with moles of electrons. We're dealing with Kelvin. And this natural log of Q. Q is the reaction quotient. That's going back to equilibrium. And that was when you would do your, if you had your reaction that was something like A is in equilibrium with making 2B. If these were both aqueous solutions, then I would say my equilibrium expression would be that K equals B squared over A. And if I didn't necessarily have equilibrium concentrations, but whatever concentrations I started with, then I would have Q. I'd have the reaction quotient where I'm at this time, checking to see am I at equilibrium, do I have too few products, do I have too few reactants. So this guy doesn't have a unit. So now I know that I'm dealing with Kelvin, I'm dealing with moles of electrons, I'm dealing with coulombs. This is in volts. If you look at the different R's on your sheet, there's about 4 of them. There's only one that has coulombs, volts, moles of electrons, and Kelvin. Okay, and that one is 8.31 coulomb volts per mole Kelvin. Okay, now you have the equation, let's try it out. So let's see, the cell we're going to use, we're going to calculate the potential difference in volts of a cell. It's going to be made from zinc and 0.1 molar zinc 2 plus, silver and 0.1 molar silver ion. So the first thing I want to do is I take my standard reduction potential sheet and I shake it, apparently. So I've got silver plus. When it's reduced, it gains 1 electron and it becomes silver. And that 0.8 volts. Okay, positive 0.8 volts. Okay. Zinc, when zinc is reduced, it goes from being a 2+, it gains 2 electrons to become zinc metal, and that guy is going to be unfavored by 0.76 volts. Okay, so I actually just did this problem, so I had it memorized. I look a lot longer than that. I see you guys struggle and kind of give up in finding the metals. Take your time. Look for the metal, don't give up. Okay, so clearly this is the more favored reaction, so I'm going to keep this in the direction it's going. I'm going to flip that. Okay, so instead of making the zinc metal, I'm going to oxidize that zinc metal. So zinc is going to be oxidized. It turns into zinc 2+, giving up 2 electrons. And as that happens, it's now favored because I'm going the opposite direction. 0.76 volts, favored versus hydrogen. All right. So if I'm going to balance this equation, I can see that silver takes on 1 electron. Zinc gives up 2 electrons, so every time zinc gives up 2 electrons, I'm going to need 2 silver ions to take on 2 electrons to make 2 silver atoms. Okay, so my balanced equation is 2Ag plus, added to zinc, makes 2 Ags, and 1 zinc 2+ ion. Okay, and then my total voltage is going to be positive 1.56 volts. All right, you know what? That's my E cell. Sorry, that's my E cell, not my E naught value. Not meaning standard conditions. Okay, so now I'm going to use that the Nernst equation to find the potential of my non-standard cell. So the potential of my cell is going to be really close to that standard potential, E naught minus RT. Do you mind if I just plug it? Yeah, I'll write it. RT NF natural log of Q. We'll plug some stuff in. All right. Actually, we have to figure out what the Q is going to be. So I have my balanced equation. I'm going to leave the solids out because in equilibrium expressions, I just use gases and aqueous things. So my Q is going to be, I'm going to have to erase a little bit of this, so go ahead and pause and copy. Okay, so my Q is going to be the zinc 2+, because that was my product, over my silver. There were 2 silvers, so I take that silver plus and I raise it to its coefficient, 2, and then I go ahead and plug some stuff in. So it was 0.1 molar of the zinc, and it was 0.1 molar of the silver squared. All right, so it's going to be 1 over 0.1, so it's going to be 10. All right, so 10 is my Q. Now I can plug in. So let's see, natural log of 10, which ends up being 2.3, minus R, so R is that 8.31. Oh, I really want to show you guys units, so I'm going to actually make sure I do all of it. Okay, so R, 8.31, and that is coulomb volts per mole of Kelvin. Okay, so it's RT, right? So 298 Kelvin. N is the number of moles of electrons that was transferred, so that's 2. F, the little curly Q F, that's Faraday's constant, so that's 96,500, and that's coulombs per mole. Okay, natural log of 10, so that's all going to be, I'll just put natural log of 10, but when you plug that in, you'll get your 2.3, you'll multiply it by this, and it was that E naught value minus this, times my natural log of Q would give me my whole E cell, right? The goal. So equals, that E naught was 1.56 volts. Okay, so here's my favorite part. So it's all been building up to. Coulombs cancels out, moles, moles, Kelvin, Kelvin. I'm left with volts. That's reasonable. I'll be adding volts to volts. I'm a happy person. Okay, So natural log the 10, you'll get something, 2.3 something. Multiply it by this guy, 8.31 times 298, divide by 2, divide by 96,500. And this whole thing ends up being a really small value, but ends up being positive. And let's see. When I end up subtracting 1.56 minus this really small value, I get the E cell. Did you get it already? Did you beat me to the answer? I hope so, because then you can feel good. Because I wasn't racing. Now you can feel good, because you know you got it on your own. Yay! 1.53 volts is what I get. Ta-da! Oh, and you know what? Let's look and see. Why don't we use that equation when we have standard solutions? So, oh, well, I don't need to change. The reason we don't use that equation if we're using standard solutions is this log of Q thing, right? If I had standard, my concentrations would be 1. So I would have 1 over 1 squared. That'd be 1. When I natural log 1, I get 0. So this whole term would be 0. So the potential of the cell would just be the standard potential. So that's why you only have to use this if you're changing the concentrations. Then the other thing, let's see. It's good to think about why this occurs. I decreased both my reactants and my products, but since there were 2 reactants showing up, the 2 silvers, I was affecting their chance of colliding, or their chance of, not really colliding, but their chance of reacting much more than I was affecting the product's chance. So I decreased it more than I decreased the products. So that's why it ended up needing to shift back towards. So that's why my potential actually decreased, because I was decreasing my reactants, making the reaction less favored to occur, and that's why I had a less positive potential. Positive potentials mean you have a reaction that does occur, but since 1.56 was larger than the 1.53, by decreasing the reactants, Le Chatelier predicts that I'll shift back towards the reactants to reestablish equilibrium a little bit, and my reaction is less favored.